Okay, so based on our reading, we know that our central theme, the very center of this whole conversation, is going to be geological time. From that point, where do we go? What else have we learned from that reading? So let's look at page 77. What are some of the things that we know from the reading that is significant or play a role in determining geological time? One of the points of emphasis is we have different types of sedimentary rock that form. So let me ask you this. Why is it that we focus on types of sedimentary rocks so much and we don't necessarily worry about igneous or metamorphic rocks? Let's think of it this way. Igneous rocks form how? Cooling of magma. That can take all of a day. Right? Done. One process, volcano, eruption, rock made. Metamorphic rocks are formed how? Heat and pressure. Good. Now, our sedimentary rocks kind of tell us a story. They can happen for a lot of different reasons, right? We talked about this, the cementing process that can occur on beaches with calcium carbonate. We talk about the cementing process that can occur based on pressure. But they tell us more about where that rock came from than a metamorphic or igneous rock is going to. I take it back. An igneous rock is going to tell us it came from some sort of magma. That's easy. But we can get more details and more inferences from sedimentary rock layers than we can from igneous or metamorphic. Also keep in mind, sedimentary rock tends to preserve the stuff it was made from, the shape of the particle, fossils. So when it preserves things and it shares more information with us, then it becomes really significant as far as the details. Okay? What else do we have? We have this individual, Nicholas Steno. Why is he significant? Go ahead, talk at your table first. But why is Nicholas Steno significant in this reading? He was the guy that provided us with understanding to, okay, if rock layers exist, what does that tell us? We see that show up in the different laws. So we have the law of superposition. He shows us that in the law of horizontality. And let's not forget that those laws explain to us, why do we see layering? Why do we see certain rocks in different levels of strata versus other levels of strata? Keep in mind words like strata or stratigraphy are still significant vocabulary that you should be using when you reference this stuff. But it also is going to give us some indication as far as if we see a fossil in a layer and we don't see it in the next, which layer relative to the next is older. Okay, so it helps fill in that gap for us. Let's take a look at page 78. What's some big take-home points from page 78? So one of the biggest take-homes from this page is that we use comparisons, right? We gather information and then we make comparisons in order to determine something. Okay, so I'm just going to write down below here comparisons because we're going to use these laws, make comparisons, and that's going to help us determine the order of events. Then we start talking about something called relative time scale. And when we talk about relative time, we're talking about a comparison of one layer to the next in order to determine which ones are older and younger. Okay? Now, scientists pull all this information together and they've developed a time scale. And that time scale can be somewhat confusing because it's broke up into specific parts. The broadest category on a time scale is what we call an eon. And let's say an eon is like it's a cheesecake, a whole cheesecake. And we decide to cut that cheesecake in half. The whole geological timescale is the entire cheesecake. But once we cut it in half, the fact that we have two pieces means we have 2 eons. One half of it is this eon, the other half is another eon. And the way our time scale works is we continue to break up or cut up our cheesecake, so to speak, or our time scale into further divisions. So now instead of cutting our cheesecake in half, we're going to cut it into 8 pieces. Okay? And that would be similar to breaking it into an era. But yet we might want to look at that era a little bit closer. Same way you looked at your time scales. You looked at it based on your 5 significant events. And then we broke up those significant events into smaller chunks of time by including 15 other events. So you take your eon, you break it up into eras. And then your eras are broken up into what's called a period. And then some of the periods are broke up into something called an epoch. Let me be very clear. An epoch is still part of an eon. It's still a piece of the eon, that overall time scale. These are just smaller divisions. So here's my cheesecake, and I know you guys love my drawing skills. So here's my cheesecake. My eon is 1 piece. My era might be 4 pieces. My period, I'm just going to keep chopping it up into more. And then our epoch is just completely chopped up little segmented pieces. But it's all the same time put together into one big, massive amount of time. It's just how much we cut it up, how much we divide it up. It changes between an eon, era, period, and epoch. And actually, there's more classifications in there because scientists like to be complicated, right? So there's actually more classifications than just that, but those are the ones that we're going to focus on. For today's activity, what we're going to start doing is we're going to start just diving into the history of the Earth. Some significant events, some significant things that happen. We're going to talk about how to build a time scale and how to break up a time scale. And you guys get to use math in here. This is the part where I find students wanting to pull their hair out. You have to use proportions in order to do this. And I'm going to pose this first question to you. You need to use the following information to determine a scale, to create a scale. Now, you guys have created scales for your maps. You've created scales previously in this classroom. So you got to kind of think in lines of how do you create a scale. And we're going to say 1 centimeter is equal to 1 million years. Okay, so 1 million years. And if I'm telling you that the Earth is 4.5 billion years old, what scale would you create? That's all the information I'm going to give you to start out. And at your tables, you need to come up with a plan. How could you create a scale? And when you create that scale, what would it be? You have 4 minutes. Go. Okay, so the first part of setting up this scale, the first thing we did was we set up a proportion. And we said that something was equal to something else. Whatever you have on top for units, on one side, you have to match on the top on the other side. Vice versa on the bottom for units, the same on both sides. So the information we know, 1 centimeter is going to equal how many total centimeters? We don't know yet, but that's what we're trying to figure out. And on the left-hand side, we're saying 1 centimeter is 1 million years. In comparison to our total timeline, in which our total timeline being 4.5 billion years is translated to 4,500,000,000 years. And the easiest way to do this, I think, is to cross multiply and then divide by what you have left. I always go that route. Now, I know in math, sometimes you guys are taught a little bit differently, but in this instance, then all I need to do is whip out my calculator, not my calendar, and say, okay, so I have 4,500,000,000 divided by 1 million equals what? So essentially, you're just moving this on top, multiplying it times whatever's on top, and then dividing by what's left. Cross multiply and divide. And in that case, we're going to find out that our answer for this is 4,500 centimeters. So if I was to write this out, I'm cross multiplying and then dividing. So what that looks like is 4,5 times whatever I have on top divided by what's left. But in this case, because it's times 1, we know the answer for that. I would hope we know the answer for that, right? And then we just have to divide by what's left. Let's say we were putting on a 2 centimeter scale, and we came up and said, okay, 2 centimeters is equal to, let me fix that. 2 centimeters is equal to 100,000 or 1 million years. Then in that case, you would cross multiply, so you'd have a 2 in here. Cross multiply and then divide. Okay, so you do have to multiply first. Whatever it's across from, you're multiplying those first and then dividing by what's ever left. Okay, so moving on, I'm going to assign each group a scenario. These are what's kind of the basics of our geological timeline, some of the premises of what we're going to start doing. Each table is going to get a different one to calculate. You're using the same scale. So we're still using the scale from the prior slide where we say 1 centimeter equals 1 million years. Okay, so that's still the setup of your proportion. The first table is going to figure out how many centimeters we would need on a timeline to show when Homo sapiens arrived. Okay, so they arrived 40,000 years ago. That's how long humans have been on the earth. So that's table 1. Table 2 is going to determine how long Homo erectus was around. And in this case, 1.6 million years. So how many centimeters would that be on a timeline? The next group is going to do the Ice Age, so group 3. So Ice Age, and your number is how many centimeters would 2 million years represent? Group 4, you're going to determine the primitive humans, so 3.5 million years ago. Group 5, you're going to take on the dinosaur extinction for 66 million years ago. And then group 6, you're going to take on the Paleozoic era 570 million years ago. If you finish early, you need to raise your hand, and I will assign you one of the remaining ones. I will be around to check your answer. So you need to raise your hand when you think you're done.